Alright, so a quick recap of Hermitian operators. A Hermitian operator A has certain eigenstates given by lambda I, denoted by lambda I, labeled by lambda I. Since this is an eigenstate of the Hermitian operator, the state is unchanged after the action, and to obtain an eigenvalue, lambda I, and lambda I is a real number, which means that lambda I conjugate is the number itself. So the eigenvalues of a Hermitian operator are real. The second important property is, alright, so if you have an n-dimensional Hilbert space, this means you will have n eigenstates, lambda 1, lambda 2, lambda 3, all the way up to lambda n. So these are all the eigenstates of the operator. So if the operator acts on any one of these states, you get the same state back again. If the operator acts on a superposition of any of these states, you don't necessarily get the same state. Is that true? So if I have, say, C1 lambda 1 plus C2 lambda 2, and the operator acts on this superposition, would the state remain unchanged or would it change? Is this state, this superposition state, an eigenstate of the Hermitian operator? Okay, let's check this out. So A acting on this state, C1 is just a number, so it's porous. So A1 acting on this state gives me lambda 1, ket lambda 1 plus A acting on this state gives me C2 lambda 2, ket lambda 2. Now can this be written as something, say, B of the original state? Can I write this? Is this state equal to this? Can it choose some value B such that this state is written as this state? What is the value of B? What is lambda? Which eigenvalue? I have two eigenvalues, lambda 1 and lambda 2. Which one of these is B? Right. So this state, which is the superposition of any two eigenstates, is not an eigenstate of the Hermitian operator in general. Okay. It will be an eigenstate only if this lambda 1 equals lambda 2. Okay. So if you have a set of eigenstates for an operator, the superposition of any 2 or 3 or 4 eigenstates is not necessarily an eigenstate of the operator. It's only an eigenstate if the corresponding eigenvalues are equal. Only superposition of degenerate eigenstates will be an eigenstate of the operator. Okay? So if these are eigenstates, their superposition is not necessarily in general an eigenstate. Only superposition of degenerate eigenstates are an eigenstate. Okay. So the first property is that the eigenvalues are real for a Hermitian operator. The second important property is that if lambda I does not equal lambda j, which means you pick two eigenstates whose eigenvalues are distinct. Such eigenstates are non-degenerate. then the corresponding eigenstates will be orthogonal. Okay? And we proved this in the previous lecture. The third important property is, suppose I have n eigenstates, which are these eigenstates. Let me rewrite these states. Lambda 1, lambda 2, lambda 3, lambda 4, up to lambda n, right? So these are the eigenstates of the operator A. Now suppose the eigenvalues corresponding to these states are lambda 1, lambda 2, lambda 3, lambda 4, up to lambda n, right? So these are the eigenvalues of the operator. Now the set of eigenvalues is also called the spectrum of the operator. The spectrum of the operator. Okay? Alright? Now if all of these eigenvalues are distinct, if all the eigenvalues are different, then according to rule number 2, all the eigenstates will be mutually orthogonal. Alright? Now if these eigenstates are mutually orthogonal and the number of eigenstates is also n and it's an n-dimensional space, then these eigenstates will form a basis for the operator, or for that Hilbert space. Any state psi living in that Hilbert space, which is n-dimensional and n is finite, can then be represented as a superposition of these states. Right? Because all of these states are mutually orthogonal and their number is the same as the dimensionality of the space, which means that these eigenstates form a basis for a state living in that Hilbert space. Okay. Any vector can be represented as a superposition of these states, correct? So any vector living in that Hilbert space can be written as some Ci lambda I summed over all i's, correct? Because all of these eigenstates, they form a complete set. They span the entire space, which means they form a basis. They are also orthogonal. Okay. And you can always normalize states. You can normalize vectors. And you can also orthogonalize vectors. I'll have more to say about this in a minute. So any state can in fact be written in this form, where these are distinct, these are eigenstates corresponding to distinct eigenvalues. Right now we are supposing that all the eigenvalues are distinct. Okay? So it's a completely non-degenerate spectrum for the operator. So any state can be written as this superposition. And what are these Ci's? These are just inner products. So each Ci is just an inner product, which means that the original state can be written as psi is inner product with lambda I with all these terms, right? Agree? Now this is just a number, so I can rewrite this as, I can bring this lambda I here, I can move this number to after the cat, I get lambda I here, I put this inside brackets, I put psi here, okay? So what should this sum of outer products be equal to? Which operator? Identity. Because the right hand side must equal this cat. Hence this must equal the identity operator. Which means that the identity operator can always be written as the sum of the outer products of all the eigenstates if the spectrum is completely non-degenerate. You choose any basis in the Hilbert space and you form this any orthogonal basis, you form this outer product and take the sum over all the indices, you will get the identity operator. Okay? So this is a general rule. All the lambda i's in this case are forming a basis. Okay? Alright. Now, question. Are all of these states orthogonal? Yes, because all the eigenvalues are distinct. It's a totally non-degenerate spectrum. This is our assumption. So all of these states are orthogonal. Their number is n, so they must form a basis. Okay? This is something you know from linear algebra. The second point is that each of these states can be normalized. There's no problem normalizing the states. Okay. So the identity operator can always be written as a sum of these outer products. Each one of these is now an operator, right? And if we have a four-dimensional system, for example, then the identity operator can be written as lambda 1 plus bra lambda 2, cat lambda 2 plus bra lambda 3, cat lambda 3 plus bra lambda 4, cat lambda 4. Okay. If the eigenvalues are totally non-degenerate and these form orthogonal states and they are normalized. If these states are normalized and orthogonal and they correspond to distinct eigenvalues, you can always form this sum and get the identity operator. Okay. Now if I have a Hermitian operator A acting on the state psi, okay. Now what I would like to do is I would like to express psi in terms of its eigenstates. Right? So A now acts on lambda I, the projection of psi onto lambda I summed up over all the i's. Okay. Now this is a sum over all the i's and A is just an operator, so I can pull this sigma sign out. I have I here. Okay. Now this is just a number. It's just a scalar because it's an inner product. So this A is actually acting on all of the eigenstates individually. So I can write lambda I psi A acting on lambda I. Now what is the result of A acting on lambda I? What do you get as a result? Aapko? What happens when this Hermitian operator acts on its eigenstate? This is an eigenstate of the operator. So what is the result for this operation? Up and up lambda I times get. Lambda I times its get. So I get this is a sum. Lambda I is just a number. I put lambda I here. Okay? And I put cat lambda I here. Okay? Now let's do something interesting. I'm just going to move here so that I can preserve some blackboard. I. Now this is just a number, so it's porous. I can move it to after the cat. This lambda I remains where it is. Cat lambda I, bra lambda I, right? Now these are the only indices, the only factors with an index I, so I can put this in brackets and all of this is acting on psi. Now if I compare with the left hand side, what should this thing be equal to? Identity?
So lambda.
It's not going to be sigma lambda. Why is it going to be sigma?
It's going to be the Hermitian operator.
It must be equal to this operator A. It's not equal to sum of lambda i's. It has to be equal to this operator. Okay? Which means that the Hermitian operator A is equal to these outer products multiplied with the eigenvalue summed up over all values of I. Okay. And we'll notice what this physically means. A Hermitian operator is expressed as a sum of the outer product of its eigenstates, where each eigenstate is multiplied by the corresponding eigenvalue. If G? Okay, I will do that. What do we see here? Suppose I have a 4-dimensional Hilbert space, right? Suppose my n equals 4. And I have an operator A living in this 4-dimensional Hilbert space. The eigenstates are lambda 1, lambda 2, lambda 3, lambda 4. And suppose the eigenvalues associated with these states are lambda 1, lambda 2, lambda 3, lambda 4, and none of them are equal. Okay? None of them are equal. Okay, so it's a completely non-degenerate spectrum. Now I know that the identity operator is equal to this, because all of these 4 states form a basis. They form a complete set. They are mutually orthogonal and they can be normalized, so they form a basis or a complete set. So the identity operator can always be written as this. Now this result tells me that the operator A can be written as lambda 1, which is the eigenvalue corresponding to this eigenstate, multiplied by the outer product of lambda 1 with itself plus lambda 2, outer product of lambda 2 with itself, plus lambda 3 with itself, lambda 4, outer product of lambda 4 with itself. Okay? Agreed? This is called the spectral decomposition of the operator. We have decomposed the operator in a certain basis itself. Generally we decompose vectors, right? This is a decomposition of a state in a basis. Okay? What we've done here, we've decomposed an operator in a certain basis. So, in the operator space, in the space of operators, vectors live in a space which is called the Hilbert space. Operators also live in a space. It's generally called the superoperator space or the Liouville space. It's beyond the scope of this text, but any operator, Hermitian operator, can also be expressed as a sum of these basis operators with the corresponding eigenvalue. Okay? This spectral decomposition of a Hermitian operator is the most important, I would say, one of the most important results in quantum mechanics. Any operator can be, Hermitian operator can be spectrally decomposed, especially when we're talking about finite dimensional systems. Okay, and this has a lot of useful ramifications as we will explore. Okay. Now the third point I would like to mention is, and remember, these are real numbers. Okay, before we move on to point number 3, I would like to represent an operator in a certain basis. I would like to choose a representation. Suppose my representation is such that lambda 1 equals 1, 0, and n minus 1, 0. Lambda 2 has a 1 in the second position, and so on. Lambda n has a 1 in the last position, right? And this column vector, each column vector is n entry. So this is my choice of basis and my choice of representation. Now I want to express this operator in this representation, which means operator A, of course, will be represented by a matrix. Now could you tell me, what would this matrix look like and what will be its entries?
It will be lambda 1 and then 0 on 0.
Right. Then lambda 2. It's going to be a diagonal matrix. Okay. It's going to be like this: lambda 1, lambda 2, lambda 3, lambda n, right? And zeros everywhere else. Okay? It's going to be 0 everywhere else. So a diagonal matrix, in shorthand, I can also write as diagonal matrix lambda 1, lambda 2, lambda 3, lambda n. Okay? So this is a shorthand way of writing a matrix. What does this mean? This means that if I use the eigenstates as the basis in the Hilbert space, then a Hermitian operator in the same representation to be represented becomes a diagonal matrix. Let me write down the statement. A Hermitian operator is diagonal in its eigenbasis. A Hermitian operator with a totally non-degenerate spectrum has eigenvalues and eigenstates. If you use your eigenstates as the basis, then that operator in the basis we've chosen will become a diagonal matrix. And the entries of the diagonal matrix are the eigenvalues of the operator itself. And diagonal matrices are very useful to deal with because they commute with everything, they're easy to multiply, and so on. And these eigenvalues, when we will discover today, are the pillar of quantum measurements. Okay, we'll learn that today. Now, the statement that I've written here, I intuitively given you. You in fact told me that this operator is going to be diagonal. Can you prove this mathematically? How can you prove it?
We have to get this so we can find the corresponding product, multiply it out.
Okay, so you have the matrix. You multiply it with the individual matrices. That's fine. But if I've given you this operator, I would like to find the matrix elements of this operator. And those matrix elements should be 1 only in the diagonal position and 0 elsewhere. So what I need to prove is that if I have this A, which is an operator and really a matrix, then the jkth element of this matrix, what should this be equal to? 0? When j equals to k, what should this matrix element be equal to? First of all, tell me, do you realize that this is a matrix, element of the matrix? Right? Kth row, kth column. Now, if this were true, what we've seen that written in the eigenbasis, the matrix element, if the matrix is diagonal, what should this element be equal to? 0 all the time? Unless j equals k. And when j equals k, what is its value?
1.
It's not 1. It's lambda j. Right? It's lambda, when j equals k, then its value should be lambda j or lambda k, because j equals k. So you can write lambda j delta j k. Okay? The jkth element of this operator, of this matrix, should be equal to lambda j into delta j k. ये समझे? यार ये एक ऐसा नंबर है, एक ऐसा फंक्शन है, अजीब सा फंक्शन है जो वन वैल्यू ले लेता है जब ये दो इंडिसेस बराबर होते हैं, और अदरवाइज ये जीरो ले लेता है, ठीक है? But we know that this jkth element of an operator is simply the operator, and you take the inner product such that you get write bra j here and get k here, right? This is the jkth element of the operator. Okay? Since we've chosen a representation, this j is really lambda j. This is a. This is lambda k. Okay? And we have to prove that this element equals this. Okay. So this lambda j, bra lambda j, is written as it is. A I pick up from there. Lambda I, cat lambda I, bra lambda I, cat lambda k.
सर उस स्टेप से नीचे उस स्टेप पे कैसे होगा?
मैंने भी ये हमने प्रूव करना है.
प्रूव करना
जी. तो मैंने ajk is the jkth element of the operator A. We know that the jkth element of operator A is this. Okay. This is something we dealt with in the previous class. And now we're going to solve this. Now since this is a sum over all of i's and there is no I appearing anywhere else, this sigma sign can be taken out. And I can write bra lambda j lambda I lambda I lambda j. और ये साथ ठीक है lambda I, the eigenvalue lambda I. Okay, now these are orthogonal eigensets. Okay, hence this number is non-zero only when j equals I and I equals k. So only one I is picked, the I that equals j that equals k. Only one of these is picked. And so I can replace all the I, j, k by a single variable, say j or k. And this is the same as writing lambda j delta j k. Okay? Or I can write lambda k delta j k, doesn't matter. Only one of these i's is picked, is selected. Because otherwise this term will become zero. Hence I have shown that the operator is diagonal in its own eigenbasis. In its own eigenbasis means the basis that is made up by its own eigenvectors. तीसरी चीज जो ऑपरेटर्स हेर्मिशियन ऑपरेटर्स के बारे में जाननी जरूरी है वो थोड़ी सी ट्रिकी है लेकिन इतनी मुश्किल भी नहीं है. Suppose my eigenvectors are lambda 1, lambda 2, lambda 3, 5, 4, right? You make, what does it 5 now? 5, 5. Lambda 6. Lambda n. Okay? So suppose these are my eigenstates. And the eigenvalues are, of course, lambda 1, lambda 2, lambda 3, and these are all different. Okay? The eigenvalue corresponding to 5, 4 is lambda 4, and the eigenvalue corresponding to this is lambda 5. But it turns out that these eigenvalues are equal. Okay? And lambda 4 or lambda 5 is unequal from everything else. But lambda 4 and lambda 5 are two eigenvalues that are mutually equal, but they distinct from any other eigenvalue. Okay? So we have lambda 6 here. This is lambda n. Okay? So now we don't have a completely non-degenerate spectrum. Two eigenvalues are mutually equal. So two eigenstates, 5, 4 and 5, 5 are degenerate. These are two different eigenstates that have the same eigenvalue. Is the identity matrix Hermitian? Irfan? Identity operator Hermitian होता है? Complex conjugate the transpose. It is Hermitian. And what are the eigenvalues of this unit operator? They are all 1 and they are all equal. So the unit operator is an example of an operator which is Hermitian, but it has a completely degenerate spectrum. All the eigenvalues are equal. So quantum mechanics tells you that if your eigenvalues are equal, then the eigenstates need not be orthogonal. But there is a procedure in linear algebra that is called Gram-Schmidt orthogonalization. Gram-Schmidt orthogonalization. Right? Have you studied this procedure? No one gets it. Alright. You can look up a linear algebra book and I'll upload 1 or 2 pages as a proof. But it is always possible to take up these eigenstates, which have the same eigenvalue by the way, and form combination of these eigenstates. For example, I can form C4 5 4 plus C5 5 5, right? First question. 5 4 is an eigenstate of the operator A. 5 5 individually is an eigenstate. Is this combination an eigenstate of the Hermitian operator? Yes. Why? Because they are degenerate, they have the same eigenvalue. You pick up any two other eigenstates which are mutually orthogonal and form their superposition, it will not be an eigenstate of the operator. Okay. Only these lucky 5 4 and 5 4 happen to be such that since they are degenerate, their linear combination will be an eigenstate because they have the same eigenvalue. So let's call this state lambda 4, right? Lambda 4 is an eigenstate. Okay. Likewise, I can create another superposition D4 5 4 plus D5 5 5 and call this lambda 5. Okay. Now it turns out that these coefficients, the C's and the D's, can be chosen by an algorithm called the Gram-Schmidt orthogonalization procedure such that these states, which are eigenstates of the operator, they are mutually orthogonal and they are normalized. Okay. So for a Hermitian operator, it is always possible, whether you have a degenerate or a non-degenerate spectrum, to choose a set of eigenvectors that are mutually orthogonal, normalized, and hence they form a basis. Okay? So even when the spectrum is non-degenerate or degenerate, you can always choose a set of eigenstates which form a complete basis, which form a complete set, which totally span the Hilbert space. So instead of these 5, 4 and 5, 5, I can always choose lambda 4 and lambda 5. And now this set of all the lambdas will form an orthogonal set, which forms the basis of the Hilbert space. Okay? So,
High basis can the disaggregate on.
ठीक है? मिसाल के तौर पे unit operator है. It lives in Hilbert space. All the eigenvalues are degenerate, but you can choose n mutually orthogonal eigenstates for the unit operator, which are simply one, zero, zero, 0, 1, all of these states, they form a basis of an n-dimensional space, and they are the eigenstates of the unit operator. Even though the unit operator is completely degenerate, all the eigenvalues are equal, each eigenvalue equals 1, but still these eigenstates are all mutually orthogonal, and they form a basis for the Hilbert space. Okay? So, why are Hermitian operators important? Why are Hermitian operators so important? This is a question we like to now ask. So any questions from your side? Suppose I have a box and it comprises photons, a set of photons, electrons, neutrons, subatomic particles that are obeying the laws of quantum mechanics. For example, they exist in superposition, something that cannot happen classically. You have a superposition of two orthogonal states, alpha plus beta, right? Quantum mechanically, you can have this state where alpha and beta are mutually orthogonal. Classically, you're electrical engineers, most of you, even you're physicists, you work with transistors. Now, if I have a circuit, okay, you put a certain current in here into a transistor. This transistor can be switched on. Okay, when this transistor is switched on, okay, there is a certain voltage here. When it is switched on, this voltage becomes 0. When it is off, this voltage has to be this voltage. So there are two states for this voltage. It can either be, say, 5 volts or 0 volts. Now these are two states on the transistor. It can either show you some voltage or show you no voltage at all. It's really what is called a Boolean device. It can either be on or off. Okay. Now this state of having 5 volts and having 0 volts are mutually orthogonal. You cannot have the best of both flavors. You cannot have 5 volts and 0 volts at the same time. Okay? So these are mutually orthogonal states classically. But here we have mutually orthogonal states, say ket alpha and ket beta. Mutually orthogonal means that inner product is 0. Gradually we'll move away from the polarization description. So we have two-dimensional Hilbert space spanned by two basis vectors, ket alpha, ket beta, mutually orthogonal. Quantum mechanically, you can have a superposition. Okay? You can have an arbitrary phase here as well. That's allowed, totally permissible. Now there's something quantum happening inside. There's these phase factors, these complex numbers, these superpositions exist. Now, quantum mechanics is of utility. This is the utilitarian perspective in the philosophy of science, that quantum mechanics can only mean anything if you're able to measure it. If you're able to have experimental outcomes, if you're able to explain experimental outcomes in the way that a superposition must exist, then that's the proof that a superposition exists. How do you verify that a superposition exists? You have to perform a measurement. Okay? So there is something outside this quantum box, outside this green box, in which the Schrödinger cat is living, that is necessary to probe the quantum state. And that is what we call the observer. The observer can be a human being. The observer can be an ammeter, a voltmeter, a photon detector. It can be a piece of glass. It can be something that is outside this quantum box, which forms the surroundings of this system, that can probe the system. The environment can also be an observer. So one has to look into this quantum box and obtain what are called measurement outcomes. You have to measure the system and you have to gain some information about the system itself. Okay? Now there is a thick curtain between this boundary between this quantum system and this classical observation system, because the observation only happens classically. Okay? एक मोटी चादर है इन दोनों के दरमियान, एक पर्दा है, हिजाब है, इसके अंदर देखना ऑब्जर्वर ने, और होता यह है कि जब ऑब्जर्वर इसके अंदर देखने की कोशिश करता है, he or she disturbs the system. The quantum system is disturbed. Okay. Now this act of moving from this microscopic quantum system to the macroscopic classical system is generally called measurement. Quantum measurement. And measurement is the trickiest part in quantum mechanics. Okay? Most of the quantum mechanics breaks down when you perform a measurement. Now I will highlight this aspect in today's lecture. So we need to make a measurement, and we need to see what the measurement outcomes are. And from the measurement outcomes, can we predict what the state is? Because we have no other means of telling what the state is. So the only variables that we have at our disposal are the measurement outcomes, the results of the voltmeters, the results of the detectors. So based upon those measurement outcomes, we have to say something about the quantum state. So this is something we would like to look at now. Suppose, let's move back to the polarization description. Suppose I have a polarizing beam splitter PAHV. Okay, and some photon, a single photon comes in that is in a quantum state psi. Okay. Now, suppose there are two output channels, one for H and one for V. Okay. So it's a polarizing beam splitter. And there's a single photon in an arbitrary input state, which is psi CH get H plus CB get V. Alright. Now what we are doing here is we are performing a measurement. देखो यहाँ लफ्ज़, हर लफ्ज़ की अपनी एक हुर्मत है. अब जो मैं कहने जा रहा हूँ, उसकी वजह ये है कि ये लफ्ज़ बहुत अहम है इस चीज़ को समझने के लिए. यहाँ पे क्योंकि फिजिक्स और फिलॉसफी का आपस में ना थोड़ी बहुत बातचीत शुरू होती है. ठीक है, इसलिए मैं बड़ा केयरफुली यहाँ चल रहा हूँ, अपने लफ्ज़ों को बड़ा सोच समझ में बोलूँगा यहाँ पे. What we are going to do here, we have a quantum state and we want to perform a measurement. What do we want to measure? There are different things. ठीक है, so our observable, जिसको हम देखने जा रहे हैं, ठीक है, उसको कहते हैं observable. वो है polarization of the photon. Okay? और इस observable को मैं एक P से जाहिर कर देता हूं. ठीक है, इस तरह का P लिख देते हैं. Cyrillic style में. Cyrillic is a script that is no longer used. It was spoken in Mesopotamia. So this is a Cyrillic P, which represents polarization, which is our observable here. Now the next question is, I'm going to measure the polarization, which is my observable. I represent it by P, but there are different ways in which I can measure polarization. Here I have chosen a beam splitter that splits the beam or the photon according to the horizontal and vertical channels into the horizontal and vertical states. And we also know that these states are mutually orthogonal. But that's not the only way in which I could perform this measurement. I can measure polarization in an infinite variety of ways. For example, I can measure polarization using a 45-degree polarizer. The same state comes in, but now my output channels are 45 degrees and minus 45 degrees. Right? I can choose any other possible combination. I can choose PA theta, in which my input state is still the same, but my output states are at theta and theta plus 90. Okay? Yet I can choose another possibility of measuring the polarization. I can have a PAC, right? I still input get psi, but my outputs now correspond to at R and at L. So there's an infinite way of measuring the same observable, which is our polarization. Hence, it's not sufficient to tell what the observable is. You also have to tell what basis are you measuring in. Okay? Whether you're measuring in the horizontal vertical basis, or you're measuring in the 45 minus 45 degrees basis, or you're measuring in the theta plus pi by 2 basis, or you're measuring in the right left circular basis. Because the Hilbert space is two-dimensional, but there are infinite number of bases in which you can decompose your original state. So, one, you have to tell the observable. You also have to tell the basis of your measurement. Okay? basis of your measurement. Here we are using, let's use the horizontal vertical basis. Okay? Since I have to specify the basis, I put a small HB with this observable. Okay? Now I have an observable and I have a basis in which I am going to measure. Now the rule of quantum mechanics is that with every observable, there is associated a Hermitian operator. Now, the way quantum mechanics is generally presented historically is that it's a set of axioms, okay, which are given. These are generally called the postulates of quantum mechanics. Some people like this way of describing quantum mechanics, others don't. I'm halfway in between. I generally don't like to state the postulates. This is the first, second, third, fourth postulate. And the ordering is not fixed either. So one important property of quantum mechanics is that most states are represented by this vector psi. Most states. Okay? This ket has the complete information about the object you're looking at. Everything that can be told about the object is present in this state. There is nothing that can be told about this object and is not captured by this state. This state, and being able to write this state, means that you know everything about the properties or the particular degree of freedom you're looking at. It contains all the information you can possibly draw from the state, from the object. So this is a complete description of the state. Okay? Psi is everything that you must strive to learn about, in other words. ठीक है? इसके बारे में इंफॉर्मेशन जितनी ज्यादा हासिल कर पाएंगे आप, उतना ही आप उस ऑब्जेक्ट के बारे में जान पाएंगे. This is the holy grail. You need to know everything about this. Okay? This has all that there is to be told about the properties of that quantum object. Okay? Now this is generally called the second postulate. Whenever you have an observable, you associate with that observable an operator. ठीक है? बस यहाँ पे हमारा observable था P. इसके साथ एक ऑपरेटर वाबस्ता करते हैं. ठीक है? अगर observable मेरा PHB है, तो इसके साथ एक हर्मिशियन ऑपरेटर मैं वाबस्ता कर दूंगा, एक बना दूंगा. वो हर्मिशियन ऑपरेटर उसको भी मैं observable से जाहिर करूंगा. फर्क सिर्फ ये है कि मैं हैश डाल दूंगा उसके ऊपर. बाज़ औक़ात इस ऑपरेटर को खुद ऑब्जर्वेबल कह देते हैं. A Hermitian operator, in other words, is synonymous with some observable. You want to measure the position of an electron, x, in one dimension. You associate an operator with it, which is x hat. You want to find the momentum of an electron or a photon or a neutron. You associate an operator with it, p. You want to find the angular momentum of an electron, L. You associate an operator with it. And all of these operators are Hermitian. They must be Hermitian, and we learn why. Now when we define a Hermitian operator, we also need to define what the operator does. If you talk about two-dimensional Hilbert space, how large is this operator? When we represent this operator, what's the size of the matrix?
2 by 2.
It's a 2 by 2 matrix, okay? So it has two columns. So if we want to find out what this matrix is, we need to find how this operator acts on different states. Okay? How many states do we need to choose to identify this operator? 2. We choose 2 basis states, find the action of the operator on those basis states, and we can completely determine the operator. For example, PHV operator, the basis states, the basis that we've chosen for measurement is cat H, cat V. Okay? So we need to know the action of this operator on cat H, and we need to know the action of this operator on cat V. Okay? So we have to define this operation. And if we define these 2 operations, we get a complete knowledge of the operator. Because only this will give us the first column of the matrix description of the operator. This will give us the second column. Okay? Now what we have to define. Now this is a definition that we have to make. That's why I'm doing 3 line segments here. This is a definition. Let's call this Hermitian operator the polarization operator because it corresponds to the polarization observable. Okay? Now this polarization observable acts on cat H. This must be Hermitian. Okay? The basis states are the eigenstates of the Hermitian operator. Okay? Now the answer must be cat H with a certain eigenvalue. Agreed? Now we have to choose this eigenvalue. Let's call this eigenvalue plus 1. Okay. Now cat V is also an eigenstate of this polarization operator. Remember, this is the definition that we are making. Okay. So if this were an eigenstate of this operator, the result would also be cat V. But we have to choose an eigenvalue. If we want to distinguish between the action of the polarization operator between H and V, and we must distinguish. So let's use another eigen. In other words, if this is a Hermitian operator and cat H and cat V are mutually orthogonal, then what should be the eigenvalue? Should they be the same or different? They should be distinct. Hence, I use a different eigenvalue here. Let's use -1. Okay. Now this is my definition of the polarization operator. Okay. Now what I would
So the definition of polarization operator, PHV.
Right. So the polarization operator is defined by its action on its eigenstates or the basis states in that measurement scheme. Our measurement scheme uses the horizontal vertical basis. So I would like to define the polarization operator through its action on cat H and cat V. And since cat H and cat V are defined to be the eigenstates of the polarization operator, these are eigenvalue equations, but the eigenvalues need to be distinct. Okay. Now let's move forward. Okay. First question. I have the polarization operator, which is Hermitian. Can I spectrally decompose it? Yes. Now what are the eigenstates? cat H and cat V. So what I can do is I can spectrally decompose this operator according to this scheme. Okay? Cat H, bra H, cat V, bra V. It's a two-dimensional space, so only two outer products are needed. And I would put certain coefficients here. What should I put here? Plus 1. And what should I put here? Now, if I would like to represent this polarization operator in its eigenbasis, it would be a 2 by 2 matrix. And what would this matrix look like? It would have 1 here, 0 here, 0, minus 1. Okay. This column is the output, is this output, this one. This column is this output. First question. Now, if I write this spectral decomposition of the Hermitian operator, we know that this is Hermitian. I can quickly prove this. If I just take the adjoint of this operator is the adjoint of this minus the adjoint of this. And if I have an outer product, say phi psi, and if I want to find the adjoint of this, you just interchange the symbols. Okay, psi, phi here. Okay? And this is something that you have to do on your own. And the tutorial, the drill tutorial has several examples of this kind. So, the Hermitian adjoint of the polarization operator is the operator itself, right? Hence, the polarization operator is Hermitian. Is the polarization operator a projection operator? If I take the polarization operator, find its square, which means PHB multiplied by PHB. You can quickly check that this is not equal to PHB. Cat H, bra H minus cat B, bra B acting on cat H, bra H minus cat B, bra B, right? This will actually give me, you can check this, this will give me identity. Cat H acting on this will give me cat H. This outer product acting on this will give me 0. This outer product acting on this will give me 0. This outer product acting on this will give me. So this is simply the identity operator. Hence, the square of the polarization operator is not the projection operator. This alone is a projection operator. This alone is a projection operator. But the combination is not necessarily a projection operator. Alright. So what we've done, we've defined an observable and we've defined a Hermitian operator corresponding to this observable. Now I have to draw my figure again, which corresponds to the measurement scheme. H. Okay. Now, we already know that if a single photon comes in here, it can either go into one of these channels. And this is probabilistic. The probability that the photon will appear here is, what's the probability here? Not necessarily, why half? It's CH mod square, right? And the probability that the photon appears here is CD mod square. Now remember, if you have a single photon coming in and you perform this experiment and the photon appears here, from that single experiment you cannot tell what the probabilities are. They're very important. Then you put in another photon which has been somehow prepared in an identical state by nature, and you put it through the same system. It is well nigh possible that the same photon may appear here again. Still you cannot say anything about the probability. If you want to infer what this state is, you really have to perform this experiment an infinite number of times. Okay? However, you can approximately tell what the input state is by performing this experiment a sufficiently large number of times. Because if you have large number of experiments, the law of averages will work and they will give you an idea of what these probabilities are. But just looking at a single shot, at a single run of the experiment, cannot tell you what these probabilities are. And the best you can know are the modulus squared of these coefficients. And from the modulus squared, you cannot tell what CH is. Because this modulus squared, CH mod squared, is simply CH complex conjugate into CH. If you know this, or you have an approximate result for CH mod squared, you cannot tell what CH is. Because this is a complex number, it can have some phase with it as well. So going from measurements to the probabilities are fine, but going from measurements to probability amplitudes are really difficult. And the way to do that is to perform the same experiment in another basis. But this is something I am going to give as a homework. Anyway, so you input a state, these are certain probabilities that you get. Okay. Now what we do is that if I get a photon here, I pass these photons through detectors. I have a detector here and I have a detector here. Okay. Now this is a special kind of detector. It is, suppose I am using a non-demolitive detector. Demolition का मतलब पता है? क्या मतलब होता है demolition का? तबाह कर देना, बर्बाद कर देना. बर्बाद बड़ा प्यारा लफ्ज है फारसी का. बर का मतलब हवा, बर का मतलब ऊपर, बाद का मतलब हवा. हवा के ऊपर इस तरह पत्ते बिखरे और हवा के ऊपर वो उड़ जाते हैं, सब कुछ तबाह हो जाता है. लेकिन ये एक ऐसी मेजरमेंट है जो नॉन डेमोलिटिव है, जो बर्बाद नहीं करी फोटोन को. आमतौर पे फोटोन डिटेक्टर्स ऐसे होते हैं कि फोटोन पे आके गिरता है, the photon loses its existence because it gives up all of its energy to the detector, which appears as a current spike. Okay? So if you block a beam, I'm not blocking a beam here. If I put a beam block, that means demolitive measurement. Because if the photon falls here, it's gone for eternity. It can no longer be recovered. But these are non-demolitive measurements. For example, these can be glass slabs. The photon passes through the glass slab and it gives you a glow here. But the photon continues to go on. But these are very difficult experiments, by the way, but they can be performed. So these are detectors, non-demolitive detectors. And if the photon appears here, I assign a number plus 1 to it. Okay? This plus 1 is my measurement outcome. And I assign a number minus 1 here. Okay? Now, if I perform this experiment a large number of times, remember, on different photons, but different and identical photons. Remember this. It looks like a reverse tautology. I mean, it looks contradictory. But what does this mean? एक फोटोन गुजरा, आगे चला गया. उस फोटोन को उसके हाल पे छोड़ दो. उस पे दोबारा एक्सपेरिमेंट नहीं करना, क्योंकि हो सकता है उसकी स्टेट चेंज हो गई हो. ठीक है? अगला एक्सपेरिमेंट एक डिफरेंट फोटोन पे करना, जो आ रहा है नेचर से, आपको आ रहा है, किसी सोर्स से आ रहा है आपके पास. लेकिन वो जो नया फोटोन आ रहा है, वो पहले वाले फोटोन के आइडेंटिकल है, बिल्कुल उस जैसा है, बिल्कुल आइडेंटिकल ट्विन है. So you're performing this experiment multiple number of times on different but identical photons. Now, as a result, you will get measurement outcomes. You can get plus 1, 1, plus one छोड़ दो, 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, minus 1, minus 1, 1, 1. You will get a string of outcomes, okay? One photon coming in at a time, one photon coming in at a time. Now you have to look at the statistics of these measurement outcomes. ठीक है, इसका तो statistical analysis करना पड़ेगा, ठीक है? और वो statistical analysis हम 15 मिनट के बाद करेंगे, ठीक है? 11:30. Alright, a state comes in, get side, general state. Okay, and there are two output channels. What we are going to do, what we are interested in is performing a measurement. The observable is the polarization in the horizontal vertical basis. Something I would like to emphasize again and again. You have to specify a basis when you're talking about measurement. Now there are two measurement outcomes, plus 1 and minus 1. The probability of measuring plus 1, given that your input state is psi, this we all know is the inner product of psi with the eigenstate h, right? Modulus square. Okay? This is the Born interpretation of quantum mechanics of the wave function. You find the inner product of the state which you want to measure with the eigenstate which corresponds to this measurement outcome. Okay? The result, of course, is CH mod squared. The probability of measuring the other measurement outcome, which is minus 1, given your input state is psi, the state that you wish to measure, which is called the measurand. Measurand. This is your measurand. What you desire to measure is uncertain. And what does uncertainty mean? It means there are two possibilities. You can either get plus 1 or minus 1. This is what the inherent meaning of uncertainty is. Uncertainty is a range of possibilities. It's a realm of possibilities. I'm getting two possible outcomes. Getting plus 1 or minus 1. Now, these measurement outcomes will have a spread. Okay? Now I can measure this spread. I call it delta PH. Okay. And how do I define this spread? I define this spread in the following fashion. I take the square of this spread. Okay, in probability theory, if you have x as a variable and it is spread, what you really do, you take your x, you subtract from it the average value, you take the square of this deviation, okay, and then you take the average of this square. This is what you call the variance. Okay, and you define it as delta x square. ऐसे करते हैं ना? फिजिक्स लैब में भी आप इसी तरह वेरिएंस निकालिए. ये स्टैंडर्ड डिविएशन स्क्वायर है, वेरिएंस है of a variable. You take the variable, its individual value, और देखें कि वो मीन से कितना दूर है, एवरेज से कितना दूर है. देखिए पॉजिटिव नेगेटिव ये दोनों वैल्यू लेंगे, इसलिए आप चाहते हैं कि इसका स्क्वायर ले लें. फिर आप जितने स्क्वायर्स हैं उन सब का एवरेज ले लेंगे, यू विल गेट द वेरिएंस. ओके, we use an exactly analogous procedure here. Our observable that we are measuring is PHV. We want to find the variance of the measurement outcomes. How spread apart are? What's the uncertainty in this measurement outcome? So what we do, we make this equal to the operator PHV minus the expectation value of the operator. Right? So this is the operator corresponding to this observable, the Hermitian operator. It's not a transforming operator, remember it's a measurement operator. The observable operator minus the average value or the expectation value of the operator, just like here. Then I take the square of this. Okay? And then I take the average of this. Okay? Now remember, this is an operator. Okay? Is this thing an operator? It's a number, but it's the expectation value of an operator, but itself it's a number. So now I have an operator minus a number. When I write something like this, there is an identity hidden here. Okay? Hidden. You don't normally write it, but there is a hidden identity here. Okay? So now let's expand this. I have PHV minus PHV, which is expectation value squared. Okay? Now let's find the square of this. This gives me the square of this operator plus the square of this expectation value, okay, minus 2 PHV operator multiplied by the number PHV, expectation value, and then the average of all of this. ठीक है, याद रहे यहाँ पर एक छोटा सा आइडेंटिटी है जो मैं बार बार नहीं लिख रहा क्योंकि ये एक नंबर है. एवरी एलिमेंट मस्ट बी एन ऑपरेटर ऑफ द सेम डायमेंशंस. ओके, सो नाउ आई टेक दिस ये वाला ये नहीं रखा. और now I have a sum of different operators and I am finding the average value of the sum. So the average value of the sum is the sum of the average values. So this becomes PHV plus PHV minus. Now this is a number, nothing happens, the average of the number is the number itself. So just you have to find the expectation value of the operator. समझ आया ये बात? देखो Now this is equals square minus देखो इनमें फर्क क्या है? This is the expectation value of the square of the measurement operator. This is the square of the expectation value of the operator. Okay? So if I have an observable P, HV, and I want to find the spread in the values, this is the spread that I will get. Okay? For example, if my input state were the 45 degrees polarized state, which is 1 over under 2 cat H plus cat V. Okay. I know my expectation value is 0. Right? I know that. My average value is 0 because CH modulus square is equal to CV modulus square. Expectation value is 0. So this number is 0. Right? This number is 0 because the expectation value of the operator is 0. But this number is not 0. Let's find out this number. P, H, V. I have to find out the square of the operator. But the square of the operator we've already, I think we've calculated is identity. When we were proving that this operator is not, but we've already calculated this, right? It's identity. Okay? So, इसकी expectation value क्या होगी इस operator की? बताओ? इसकी expectation value equals psi, your input state, right? This is how you define the expectation value. Okay? But this is identity. So you get, which is 1. So your spread, delta PHV of measurement outcomes squared is 1. Or your spread is under root 1, which is also 1. This is clear. If this input state is 45 degrees polarized, the average outcome is 0, but the spread is 1. So you get plus 1 or minus 1. So it's a reasonable answer. The spread in values is 1. So either you get plus standard deviation 1 or minus standard deviation 1. So this gives you the range of possibilities. So in order to define the statistics, you need the average value and you need the spread of values. Now the last 15 minutes are going to be extremely important. In the meantime, I give you 2-3 minutes just to digest all of this. Suppose you have an observable A. Okay. Some observable A. Associated with this observable is a Hermitian operator. Okay, we know this. Hermitian operator is such that the dagger of A is equal to A. Now delta of the spread in the outcomes when you measure A, the square of this spread, which is the variance of the measurement outcomes according to our formula, is given by the expectation value of the square of the operator minus the square of the expectation value. Okay? Or if you use the first definition, the principal definition is A operator minus squared average, right? Agree? This is what we wrote previously, right? This is the same as this. Okay? Okay. Delta A square equals this. Mean of the square, it's the mean square of the deviation. It's the mean square deviation. You take the deviation, square it and find the mean. Okay? Now what does this mean? This means really that you form the inner product, because you state that you wish to measure this side. You form the inner product side, the square of this. Now this is an operator and you want to find the square of this. You can say A minus A twice, right? A minus A. The square of an operator is simply writing the operator twice. Will it add? Okay. Now, if this is Hermitian, there's a small identity here. This is a number, so identity of course is Hermitian. The sum of two Hermitian operators is also Hermitian. So, this entire operator is also Hermitian. It doesn't harm if I put a dagger here, because the dagger of a Hermitian operator is the operator itself. Okay. Now let's suppose, let's call this has to be in state, has to be some state. It's not the outcome, or it's not the state that will be produced, but it's going to be some state. It's going to be some vector in the Hilbert space. Let's call it A. Let's define A minus A expectation value acting on the side. Let's call this small a. So delta A square becomes equal to the inner product of A with itself. Okay? Okay. याद रहे कि if psi is normalized, A is not necessarily normalized. Okay? Because this is not a unitary operator. It may change the norm of the vector. Okay? So it's some number here. You get some complex number, but it's not necessarily equal to 1. Likewise, if I have another observable B, associated with this is an operator B hat, a Hermitian operator, I can find the spread of B's. This will simply be equal to where I have defined ket B to be B minus the expectation value of B acting on psi gives me get B. This is how I have defined B. Okay. Now what I really want to do, I have some input state psi. I have some measurement scheme. Some measurement is going on. And first I want to measure the observable A. And I also want to measure the observable B. Of course on different but identical copies of the state. Because once I've made a measurement, I've corrupted the state, I've created a new state. I cannot proceed to measure the corrupted state, the new state. I need different but identical copies of the input. But now I want to measure A and B. For example, I want to measure the path of the photon and the polarization of the photon. Or I want to measure the momentum and the position of an electron. I have different observables. Okay? And now I want to find the spread in each of these observables. Now if I multiply both of these equations, delta A squared multiplied by delta B squared equals the inner product of A with itself, the inner product of B with itself. ठीक है? समझ गए? अब this is the length of a vector, this is the length of a vector. There is a rule in trigonometry which is called, which I give you as a homework problem, is called the Schwarz inequality. Schwarz inequality. The Schwarz inequality says that in three-dimensional, in Euclidean space, if you have a vector A and you find the length of this vector and you multiply it with the length of the vector B, this must be equal to or greater than A dotted with B, the dot product. This is called the Schwarz inequality. It holds true for quantum states as well. This is just the length of a quantum state of a vector. This is the length of a vector. And this is just the inner product between these quantum states. So this must be greater than or equal to there's a square. Okay. This is called the Schwarz inequality. Which means that delta A squared into delta B squared, the product of the variances of these measurement outcomes must be greater than or equal to this number. So there is a lower bound on the product. The product of the spreads of these variables has to be at least equal to this. It cannot be smaller than this number. Okay? If I take the square root of both sides, this must be greater than or equal to A agreed? Before taking the square root, देखो, delta A, delta B squared must be greater than or equal to the modulus squared of this. Now what is the model? Is this a complex number?
So it's a length code.
It's an inner product. It's, this inner product itself could be complex. It could have a real and an imaginary part. But you take in a modulus squared. But this number itself can be complex. Okay? So I can write this thing as the modulus squared as the real part of squared, right? Plus the imaginary part. Right? This is simply the modulus squared of the number. It's the sum of the square of the real part and the imaginary part. That's how you define a modulus squared of a complex number. Now, is this positive? Is this number itself positive? Real square is positive. This is also positive. So if I just drop this out, then still the inequality will hold. Right? So delta A squared, delta B squared must be greater than or equal to the imaginary part squared, right? Okay, I've dropped out the real part because the real part is positive always. The real squared is always positive. Okay. Now I take the square root of both sides. Delta A into delta B must be greater than or equal to. Now what's the square root of this? Is the imaginary AB, right? Modulus. Okay. Now let's look at this expression. Let's look at the right hand side. The imaginary part of a complex number is equal to the complex number minus its complex conjugate divided by 2i. Is that true? Why is that true? If I have a complex number z, it's a plus iota b, its complex conjugate is z star is a minus iota b. I want to find just b. What's the imaginary part of this number? What would I do? I will take z minus z star. I will subtract the complex conjugate from the number itself. I will get 2 iota b, and b will just be equal to the number minus its complex conjugate divided by 2 iota. So the imaginary part of this number is just equal to the number minus its complex conjugate, and the complex conjugate is simply interchanging the bra and the cat divided by 2. Okay. Now what I have to find is I have to find the inner product of A with B. Okay. Now A is, how do I define cat A? This is how I define A. So bra A is simply going to be psi. The complex conjugate of that, which is the adjoint of A minus A expectation value. Since it's Hermitian, I can just write A minus expectation value. Okay, and B is here. B minus okay. Now I can perform this multiplication. AB minus A B minus A expectation value B plus okay. So this is simply the expectation value of this operator. Okay. So this is simply A B minus A B minus A expectation value B operator plus A B. Right? Now I have a sum of terms, want to find the expectation value of everything. So I take the expectation value of this operator, A, B. Remember, this is not equal to the product of the expectation values of A and B. This is one combined operator, I have to find its expectation value. However, this is a number, so I can just take the expectation value of A. I get A, B. This is also minus A expectation value, B expectation value. Plus these are numbers, so their expectation values are the numbers themselves. This just cancels out, right? I get AB, the product of A and B, its expectation value minus the expectation values of A multiplied by the expectation value of B. This is equal to the inner product of A and B. While I rub the blackboard, you can think of what, look up the calculation of it. Okay? So I have found the inner product of A and B. What I really want to find out the imaginary part is its complex conjugate as well. Right? The inner product of B and A. So I can just change the ordering. If A inner product of B is equal to this, then the inner product of B is equal with A. What is this going to be equal to? I just interchange A and B. So it's going to be B product with A, and remember this is not the same as this because operators don't commute. However, these are sheer numbers, pure numbers. So it doesn't matter, they don't matter. Hence, if I would like to calculate this object, the imaginary part of inner product of A with B, I just take 1/2i, I write this down, AB expectation value minus BA. Okay? This cancels out. Right? But this simply equals, now I have a difference of two terms. I can write this as the expectation value of AB minus BA. Right? But what is AB minus BA?
Commutator.
It's an operator that is called a commutator of the operators A and B. So we call this thing the commutator of A and B. Commutator. commutator is AB minus BA. It's a new operator called the commutator. In general, operators don't commute. Matrices की multiplication is order specific. You change the order, you get a different answer. So commutator in general is not zero, and this is where the real power of quantum mechanics lies. Now these operators, this commutator in general is non-zero. Now we have all the bones we would like to put in the flesh. So we look at this expression. We have delta A, delta B must be greater than or equal to the modulus of the imaginary part of AB, but so I would like to find the modulus of this. 1 over 2i. Oh, of course I have these brackets here. 1 over 2i A commuted with B. Now, what is the modulus of 1 over 2i? 1 over 2. So, delta A, delta B has to be greater than or equal to 1 over 2, the expectation value of the commutator of the operators. This is called the indeterminacy principle. Or if you would like to stick to history, originally Heisenberg calculated this result for one of the observables being position and the other being momentum, and they call it the position momentum uncertainty. So it's also called the uncertainty principle. We'll have more to say about this, but last 2 minutes, just one example so that will leave slightly freshen up. Remember our experiments that we discussed, a PAHV half-wave plate at 45 degrees, another PAHV and a PA45. A state comes in, an arbitrary state goes into these two channels, H and B. These are reversed by the half-wave plate because it's like a NOT gate. Interference takes place, right? And you have two outputs, a 45-degree channel and a minus 45-degree channel. And you notice that only one of these channels is populated if you don't do any measurement. Okay? Now we have two observables. One observable is A. The observable is which of these paths does the photon take. This is one observable. The other observable is B. B is what of these outputs does the photon appear at. Okay. Now if I don't observe A, which means I do not put any detectors here. There are no detectors here, right? There are no detectors here. I know nothing about the paths that the photon takes. I am completely uncertain about the path of the photon. There is a large spread in delta. There is a large delta A, which means I don't know which path the photon is taking. This delta A is large. Okay. But now I know for sure that the photon is taking one of the paths. However, if I put a detector here, a non-demolitive detector, I can tell which path the photon has taken. So I have reduced delta A. So if I reduce delta A by gaining some information about the path of the photon, that is, I have reduced delta A, I have reduced the spread in the measurement outcomes. I pinpointed which path the photon is taking. Then the spread here increases. So now I get a photon here sometimes, now I get a photon here sometimes. So I would like to leave this discussion here, and I would just like to mention that two observables that do not commute. You cannot have arbitrary precision in both of these observables at the same time. There is a seesaw effect. You have to sacrifice precision in one observable if you would like to gain precision in another observable. And this has nothing to do with your instruments. All of this description is instrument independent. It has to do something with the observables and the quantum state that you measure. So this is a limit that is set by nature, by quantum mechanics. No matter how expensive a laboratory you will build, you will never be able to bypass this indeterminacy principle. So see you on Monday, inshallah.